we're going to learn about the perpendicular bisector theorem and the angle bisector theorem. 5.2. Perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. We'll look at a picture and talk about that in just a minute. We'll let you copy that now. The converse of this statement says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of that segment. And again, we're going to talk about this. You start to see that I've got a picture drawn here. What this first theorem is saying, if a point is on the perpendicular bisector, then it's equidistant from the endpoints. So they're saying if this red line here is perpendicular and exactly in the middle of this segment AB, so this point right here we'll call M as the midpoint. So that makes that red line the perpendicular bisector of that segment, right? You agree with that? Mm-hmm. Then what it's saying is any other point you pick, if I pick this point here and call it P, the distance from P to A, so this distance right here, is going to equal the distance from P to B. What kind of a triangle will that be then?
Right triangle.
I meant the two green lines and the blue line.
Isosceles.
Isosceles, right? So a few days ago we learned about isosceles triangles and all the special things that go with it. Now this perpendicular bisector theorem is saying that anytime I know I have a perpendicular bisector to a segment, then any point I pick on that perpendicular bisector is always going to be equidistant away. So we're always creating isosceles triangles. Okay? We're always creating isosceles triangles. So the key is it doesn't matter where you pick your point. If I went down here and I picked a point right there, if it's on that perpendicular bisector, then the distance from A to that point is going to equal the distance from B to that point. Always. So if they did this, and they said this distance here is 10, what's that distance there going to be? 10. Okay? Equidistant. Always. All right? Now, I clean that up. Now, I know that P is equidistant from A as it is from B. If I know those distances are equal, then that means P has to be on the perpendicular bisector. Okay? That means P has to be on the perpendicular bisector. That's what this converse is saying. If this distance from here to there is equal to this distance from here to there, then this point must be on a line. It must be on a line that contains the perpendicular bisector to that segment. Okay? It must be on a line that contains that perpendicular bisector. And so that's what the converse is saying. All right? So, question for you. If I pulled a ruler out here and I said, Jeff, you like to play around, be a funny guy, would you come up and take a chance that you might be a funny guy up here, and would you measure the distance from that point to the line for me? be brave. Would you for me? Alright. We'll use the metric side of that so we could, it's everything's in tenths, so it'll be easier to measure. So you can just grab that, right? If you grab that edge, you can swing it. Only one touch. Let's see, if you just grab the edge of this, you can swing wherever you want, and then grab in the middle, you can move it around wherever you want. Right there, okay, how far is that? Oh, come on. Use the metric, let's just say 8 point what? 2, 8.2. So Jeff says this distance is 8.2. Let's actually move that over here so it's out of the way. Okay? That's Jeff. I need another volunteer. Come on, I need another one. Jump up here. Come on, girls. Equal opportunity here. Come on, don't make me call on somebody. Mr. Fouch here watching and you guys are refusing to participate. Making me look bad. Brandon, get up there. Measure the distance from that point to that line for me. We'll see how well Jeff did. Oh, that makes, hold on. Let's do this. There you go. If you touch that bubble, it makes your ruler bigger, it changes how you measure. So just touch the edge if you want to swing it. No, the bottom edge. There you go. What'd you get? 8.15. Okay. I know Emily's been eyeballing this, and she did this. She got 9.3. All right? So Emily was thinking 9.3. She agrees. Okay? Now, what's wrong with this?
It's not perpendicular.
Okay, so what we're saying is, if we don't have some kind of guideline, some kind of rule to measure the distance from here to there, then we could get all kinds of numbers, couldn't we? Okay? Your road that's outside your house is pretty long, right? And if you're going to put a driveway from your house to your road, the length of that driveway could vary, couldn't it? Depending on where you entered the road at. The important thing is that we have to understand that to measure the distance from the point to a line, we have to use the distance that is perpendicular. Okay? We have to use the distance that's perpendicular. So, the way to do this, I'm going to create a perpendicular here. Okay? And so, if I put that on there, well, before it wiggled at the end, would you agree that it was pretty close to perpendicular? And so, what is our distance there? I get 8.2. Alright, now, why, yeah,
Couldn't you have just picked the shortest measurement that you could find and then
you could, but how do you know where that shortest measurement is?
using the ruler?
Yeah, but my point is, my ruler, I could go along like this, and it's hard to determine where the shortest part is right there, okay? But that's the right idea. Now, I wish I would have looked at when Jeff measured a little closer, because I know he got 8.2, but I didn't pay attention to this. And then Brandon come up and changed the measurement on the scale on the ruler a little bit when he went like this. See, now I get 6.7. You see what I'm saying? So I don't know exactly what happened there. When Jeff measured it, he wasn't far off, but he was a little bit up into here, I think. And then you could see when Brandon measured, he tried to find that perpendicular. And I don't know if it was intentional or accidental, but he actually was doing a pretty good job. And then Brianna nailed it. She said that the distance from a point to a line is the length of the perpendicular to that line. Okay? So it's really important that we understand when you measure from a point to a line, you have to be measuring perpendicularly from that line. Is anybody at all confused on what we're saying right here? So if I gave you a point and a line, and I said measure from the point to the line, tell me how far it is, you're going to make sure that the line you're measuring with is what? Perpendicular to the line and passes through the point. Okay? So we're going to talk also about an angle bisector theorem. I'm going to let you copy this down and the converse of this down, and then we're going to draw a picture. I think I have a picture drawn here, and we're going to make sure we understand what it's saying, okay? All right, so this first one says, if a point is on the bisector of an angle. So if I have a picture and I have these two, sorry. I have these two little marks right here. What do those little marks mean?
Corresponding.
No, not quite. If I have a single little mark in the arc of an angle, what does that mean? Maybe you can't see from where you're at very well. So if I have these two little marks right here, well, yeah,
Angles are congruent.
it means those angles are congruent. Sometimes they put a little line in there, like that. Okay? Sometimes they do that. Sometimes they put two lines in there, like that. All right? Sometimes instead of two little marks like that, they use two little marks like this. Okay? So what they're saying is any angle that has that identical mark is going to be congruent to any other angle that has that identical mark. So if these two little marks are the same, that means those angles are congruent. So that makes that red line what to that big angle ABC?
Angle bisector.
The angle bisector. So if this line is cutting this big blue angle, angle ABC, into two equal little pieces, then that line is the angle bisector. Okay? So if that's the angle bisector, what this theorem says is that any point on that line has to be equal distance from the sides of that. Okay? The reason we took a moment to play around with measuring is because I didn't want you, I didn't want you to take your ruler up here and try to measure from A to P and get 3 inches there and say that that point P is 3 inches from the line BA. Okay? Ariana, why don't you set that on my desk, please? And so, remember, it has to be perpendicular. And so when we measure this distance, we want to make sure that it's perpendicular. oh, Mr. Fauch is saying, what is he doing? What a bonehead. Sorry, I was making it perpendicular to the wrong line. There we go. I was making it perpendicular to the angle bisector instead of the side of the angle, okay? And so I think I'm pretty close there now. I can get my protractor out and measure it. But my point is, to do this, I want to make sure that I am creating the perpendicular bisector, or the perpendicular to the side, okay? So when I do the same thing over here, I get that. And what this is saying is that this distance is going to equal this distance, okay? So if I mark those points M and N, then we're saying that MP is equal to NP. Remember, no symbol over the M and P means that we're saying the distance from M to P. And no symbol over NP means the distance from N to P. Okay? If I did this, I'm talking about the segment, the picture. Okay? If I do this, I'm talking about the ray. If I add this, I'm talking about the line. But no symbol at all. No symbol at all means that I'm talking about the distance. Okay? It's important that you remember that. And then it's also important that you try to write things properly that way. So it's, you know, it'd be like saying, I'm going to write a letter talking about what I did last night, and I use words that don't have anything to do with what I did last night. You wouldn't communicate very well, would you? So, same thing happens in math. If you don't write things correctly, then your communication falls apart. You bring something up to me, and you say, I don't get number 5, and you've not copied number 5 down wrong, and I didn't look at the book. I'm going to explain how to do what you had there, and guess what? When you're done, you still don't get number 5 because we didn't do number 5. We did whatever I saw in your paper. So it's important that you communicate by writing properly. So please try to make an effort to do that, okay? So this theorem says that any point that's on this line, right there, any point that's on that line is going to be equal distance from the side. So if Brad comes up and says, well, what about that point right there? And I call it O. And I say, oh, well, that's going to be equal distance from the sides also. Okay? As long as I draw my segments that are perpendicular to the sides, those distances are always going to be equal. The book's going to throw something in here like this, or I should say the authors of the book. If this is x and this is 10, what's x? 10. Okay? If this is 2x minus 4 and this is 10, what's x going to be now?
7.
So what do I need to do to figure this out?
2x minus 4 equals 10.
I'm going to say 2x minus 4, that's this side, is equal to this side, which is 10. And so I'm going to add 4 to both sides. And I get 2x equals 14, and I'm going to divide by 2, and I get 7. So awesome job, those of you who were shouting out 7. Okay, x is 7, that's correct. Okay? Good. You know, I almost took yesterday's lesson off the internet because I got to 5th period and I was going through the example, and I thought I had exactly the same example, and I got a totally different answer, and I thought, oh, no, did I really forget to distribute? I can't leave that on the internet. I did that wrong. And so I went back and I looked at it, and I accidentally changed the problem slightly. And in doing so, my memory was telling me I had the wrong answer. So luckily, I didn't make anything that big of an error and post it to the internet. So any questions on how to solve that? All right. The converse is just doing the reverse of that. It's saying that if I have this angle I know that this distance is equal to this distance, okay, and I have to know they're perpendicular. If I know those distances are equal, then what's that tell me about these two angles? They have to be congruent also. Those angles have to have the same measure, okay? So if they told me this was 3x plus 4, and this is 5x minus 6, then to solve for x, what would I write, Hunter?
3x plus 4 equals 5x minus 6.
So 3x plus 4 equals 5x minus 6. And then we'd move the 3x over, subtract 3x from both sides. So I get 4 is equal to 2x minus 6. Add 6 to both sides, I get 10, right? And divide by 2, so x is 5. Okay? So if you're thinking 5, awesome job for being able to do that in your head. You have to be careful though. You try to do too much in your head, sometimes you get confused. I actually looked at that and was thinking I was going to get a different answer until I started working it out, and then I realized what I'd done wrong in my head. So just be aware of that, okay? On a quiz or on a test, make sure you actually do a little bit of the work for two reasons. One, I can see what you're thinking. And the key here, what I'm really looking for here is, do you know this relationship? I'm not really grading you on how well you can solve an equation, although believe me, I hope you can all solve an equation correctly by now. But the fact of the matter is, the most valuable part of what we're learning right now is, do you know this relationship? That because these are perpendicular and equal, that means these have to be equal. Okay? So that's what I'm looking for. Alright, let me pause for a second. So on 1 through 29, you'll get 15 problems to practice those two concepts. I don't see a lot of them like we just did, but I know there's a quiz question like the ones we just did. So make sure that you pay attention to those as you do those few, okay?